Hello everyone, it's April the 9th. We have solved 777 problems. Very nice. Alright, so what we're gonna do, I first solve this one. I think we solved this one before, and then we're gonna handle the difficult question from last contest. Alright, when did we solve in the past? July 2020. Given an array of nums and an integer k, return the k most frequent elements. Oh, I see. Your algorithm time must be better than O n log n. Yeah, you sorted it and no. I mean, shouldn't that be return counter nums dot most common k? It's not right. I know it's not right because the output is going to be a weird output. 1 3 times 2. So we're going to take the first one. So say for value and count in, or we're just going to need a value. Yeah. All right, let's try not to do it this way. So what we're gonna do is return a k most frequent. So we're gonna sort, right? So basically, that's the same thing. How else could you do it? You're gonna use a hash map, right? Which is a counter, and then you're gonna sort the counter. What else can you do? And that's O1 log n and most O1 log n. I mean, we can do it manually, but what's the point? All right, what's the point when you can do? Yeah, I don't see the point. I don't see the point. From collections, import counter. So 374. I think this one is 347. It's harder than the easy one from yesterday. Counter suffices. That's it. I'll look at the solution, see if there's any smarter way. A heap. How do you do this with a heap? You have to count it first, right? Yeah, you have to do this, and then you do heap. O(n) log k. Well, it's the same. We do O(n) and then we sorted it. So it's the exact same thing. What's that? Heap.enlarge. Oh, really? Heap has this. Ha! I might as well just do counter. Quick select. That's way too complicated. But you can get to O(n). Outperformer. Huh. O(n) is a bucket sort. I mean, quick select. Because when you do this, it's saying this is kind of sorting it. So you just don't sort. You put that in a heap. So the max come out. So you just do a log k times. Well, k log n. All right, k log on plus k log n. So that was the n log k. I thought it's k log n. Well, take on to build, and then convert into an output array. Just on log k time. So on I don't understand. Why does on log k? We want to get the k most, right? And we have to do it. Basically, just pop, right? You basically just pop. You put that into a heap, and then you just pop. How many times you need to pop? You need to pop k times every time. I think it's OK log n instead of on log k. I don't understand. All right, let's say kth smallest, kth largest, kth most frequent, kth least frequent. Chooses a pivot and defines its position in a sorted array in a linear time using so-called partition algorithm. Pivot is on its perfect position in an ascending sorted array sorted by the frequency. All elements on the left are less frequent based on frequency than the pivot, and all the elements on the right have more frequency than the same. The array is now split into two parts. If by chance our pivot element took n minus k final position, the k elements on the right are these top k frequent. Hold on, so k goes 3. Build a hash map element. Okay. Elements, so these are elements, these are the counts of the elements. So choose a random pivot, usually we choose the first one, right? And put it in its place in a sorted array on the left. So the frequencies are the indices. So wait, hold on. More frequent or of the same frequency. So pick 1. 1 has frequency of 3. So we put, wait, hold on. How do we do 4? 3 put in here. So 1, 2. 1 is 3. 2 is also 3. 5 is 4. What is this perfect pivot position? The count is the index? Wait, hold on. What are we looking for? Top K frequent elements. So find one with a frequency. We put it somewhere, right? And then no, it's actually, let's say, if frequency is, let me write it out. So what we have is starting with 4, 5, 2, 1, 3, and frequency is 1, 4, 3, 3, and 2, right? So I say, usually to pivot, I choose the first one as a pivot. So anyone smaller than 4, go to the left, and nobody's smaller. Okay, so now pivot if I'm 5. So anyone, yeah, smaller than 5. So 2 is smaller than 5. So yeah, usually this one gets out. Okay, 5 with 4 frequency. So 2, so 2 comes here. Right, actually gonna swap. Right, and then for the next one. Wait, hold on. So it should be, if it's smaller. No, it's these. Hold on, let me do it again. 5 and 4. No, this is quick sort. Quick sort. And the reason again, quick sort. I forgot a quick sort. 4, 5, 2, 1, 3, right? So quick sort requires it's not. It's we find a pivot, right? So the first one is a pivot, and then it's already in position. So now we have the remaining to the right. Now we pick, always the first one is the pivot, okay? First one is a pivot, and then if it's smaller than, then we leave that is. And now we go both sides. Oh, yeah, remember, it's 2 pointers, both sides. If the left is smaller, the left just keep moving until the left is bigger, right? Until the left is bigger, then we will swap. So small, small, small. They're all small. They're all small. So when we're done, then what we're gonna do is swap, because these are smaller than, right? So eventually we'll end at a position, it's the last position where the value is smaller than this, so we're gonna swap. So okay, so swap. So 5 come here, 3 come here. Okay, so we're gonna check if we have k to the right, and the answer is no. So the answer is no. Then we have to keep looking this, right? And keep looking this part. Wait, hold on. Yeah, we split into 2 halves, the left and the right. But if the pivot, we have something on the left and something on the right. If something on the right is larger than k, then we just focus on that, right? We don't have to focus on the left. If something on the right is smaller than k, then we're gonna, we need to focus on the left. We don't have to focus on the right. So focus on the left now. So on the left is 4, 3, 2, right? Because 4 is in the right position. So 4, 3, 2 again. 3 is the current pivot. So if it's, so now when look at left and right, and then it's bigger, then we're gonna swap with the right, and then after swap, the right move forward. Now we check again. Now we break out. Right, now we break out. And now, once we break out, when I check this value, that's 3. So we have 1, 2, 5. It's a bit convoluted. Oh, I picked this, put it in the right position, and I'm going to sort this. Partition. I remember this. This is the same. No, I'm not going to implement this. Screw that. You have a counter, you have everything, right? And then you just want to make it a little slightly faster. What's the point? That was the point. And this one use selection bucket sort. How should I say it? Bucket sort. Bucket. Let's see how he does it. Bucket sort. So a bucket. So each one is frequency. Yeah. And then this is the counter. And then for each number and frequency, bucket frequency, put a number in there, and then we're going to flatten it. Huh. Why you do that? Just yeah, it's all right. We're done. We're done with this. All right, let's take a look at this. Encrypt and decrypt. Given a character array containing unique characters and a string array values containing strings of length 2. You're also given another string array that contains all permitted original strings after decryption. You should implement a data structure that can encrypt the zero-indexed strings. The string is encrypted with the following process. For each character C in the string, we find the index I satisfying keys I equals C in keys. You're given a character array, keys containing unique character, and a string array, values. Containing strings of value 2. So that's the keys. Man, this is so convoluted. I don't even understand. So this is the input, right? And its input we have, this is the first part. Have list of str, list of str, and a list of str. And then encrypt. Okay, and you're encrypt, so we pass in this. That's, what is that? This has 2 of this. That's not right. This is a single one. It should be a single one. This does not exist. So that's the keys. This is the values. and these are dictionaries. Okay, so I have keys, values, and dictionary. For each character C in the string, which string I'm talking about? These one, right? We find the index I satisfying keys. Where are the keys? Keys are this. Keys I equals C. Replace C with values I in the string. So wait, hold. Replace C with values I in the string. Oh wait, this is the string. Come again. For each character in the string, that's the string, find the index I satisfying keys I equals C. So we find this one that's in here, and then we replace C with values, one of these values. Okay, a string is decrypted with the following process. For each substring S of length 2 occurring at an even index in the string, we find an I such that values I is equals to S. If there are multiple valid I, we choose any one of them. This means a string could have multiple possible strings it can decrypt to. We find I such that values I replace S with. And what does dictionary do? Contains all permitted original strings after decryption. What does it mean, all permitted original? Returns the encrypted string. Returns the number of possible strings or two could decrypt to that also appears in dictionary. Ah, that's what dictionary is for. Example 1. So we have, these are the keys, and these are that, and this is a dictionary. Encrypt. Wait, encrypt ABC. Oh, that's the first passing. Okay, that's the first passing way. Encrypt ABCD. Okay, so A corresponding to this, so that's EI, right? ZFEIAM. So I'm gonna return that. Okay, and then decrypt this. So EI we're looking for, we have 0 or 2, right? So which means the first position could be 0, could be A or C. So we can start with A or start with C. And ZF is 1, so it's a B. AM is D. That's a possible string encrypted after decryption. So it could be, so we have this position. So EI can either be, oh, we have two EIs, remember. So EI could be A or D. right? A or C, right? So basically we have either A or C, and the second position ZF is B, third position is A and C, and last position is D. So we have ABAD, ABCD, CBAD, and CBCD. And then we need to find how many exist in the dictionary. But that's fine. Dictionary can turn that into a set and loop through all possibilities. How long does it take? All possibilities. Okay, so key length and value length is 26. And the key length is equal to value, and that makes sense. Value is 2. Dictionary is 100. 100. All keys in dictionaries are unique. Word 1, word 2. All word 1 I appears in keys. Word 2 length is even. In lowercase, almost 200, at most 200 calls will be made. Okay, so the encryption is deterministic, right? Because all the keys, all the values are unique. All the values are unique. So, but they didn't say, word 1 appears in keys. Every word 1I appears in keys. So it's, and it's unique. So every one, we find it and then we look for, and that is actually easy. That's actually easy. So what we can do is, because it's also unique, so we can create a dictionary. That's the key and that's the value. So we're just looking here, we grab it. So the first encrypt is triple, right? Encrypt is triple. Now decrypt, we can create a reverse dictionary where the keys is this and the value is this. And then because we can have the same value, so the one key, one of this value can have multiple keys, right? So when we get it, then that's what we get. We'll get a bunch of different possibilities at each positions, right? That's what we have. Then we need to know how many of these combinations exist in the dictionary. What would be a better way? But remember, because the word 2 length is 200, right? So we're going to translate to as a 100 in length. But it could be more. Right? It could be more. I can have like a lot of different options for each letter position. So it's exponential. So the better way will be to loop through that 100 values in the dictionary. That's fast. And for each one, we check if that fit. So kind of a reverse. We don't try to get everything from the decryption to the dictionary, but we go from the dictionary to decryption. Now, from dictionary to decryption, dictionary has a value. The decryption, how do I compare these two? Letter by letter, right? So in a decryption, because after decrypted, it's just going to be an array of size at most 100. And at each position, we can put a set of values, a set of letters that's allowed in this position. And then we just go one by one, right? It's just 100. 100 by 100. Oh, shoot, 100 by 100. We may need to make a decision call. Because if we go this way, go from dictionary to this, right? If we go dictionary to this, then it neither depends on which one will be faster. So dictionary to this is we'll get the length, right, times the total. That's the total number of operations. Well, actually, for each one we go 4 times. Yeah, so that's this times this, so we get the operation. And then we can also just create all possible create all possible I don't know. It depends, right? It depends which one is easier. It's easier to go from, maybe we can check, yeah, we run or calculate the number of operations needed. Or maybe there's a better way. Maybe there's a better way. 100, right? How many of these will have repeats? I can have lots of repeats. Let me think again. So it could be like, could take, let's say, make this into a queue. Okay. So every time make this into a queue. And then we check the first letter. If first letter is good, we push into the next queue. And if the first letter is not the same, then we just discard it. It means it's not possible. So in this case, this in queue, in queue, in queue. And this one's out. This one's out. Out, and in. So we'll have 4. 1, 2, 3, 4. Right? The next level is going to be B. So we check. Oh, B in, out, in. First, third, like A or C. So in, and D in. So we get. Okay, let's try this idea. Let's try this idea. Is that 7? 2, 2, 2, 2, 7. All right, so we have to a couple of things need to be coded first. All right, initializing. So we need, let's go default dict from collections, import default dict. All right, so we have 2 dictionaries. So I'm going to say self dot key to value. So KV, right? Key to value equals for KV in zip keys and values. And we're just going to do key equal value. Okay, so that's the first one. And the second one is self.vk, value to k, value to key. So it's just going to be default dict of what? What? It should be a set, right? Wait, hold on. Is that a set? It's just for each one, what are the possibilities? Yes, that's going to be a set. And then we just say, again, for, right? And then we say self.vk value.add key. So that's the 2 Once we're done, encrypt will be easy. Just for w in word 1, right? Self dot key to value w, and return dot join. This whole thing. So that's the first one. Now the decrypt will be slightly trickier. So self dot dictionary equals dictionary. So this one we can grab, let's say, decrypts shall equal to, again, for w in word 2, we're gonna go self.vk, right? Value the key, and then we have values here. Oh, that's not right. But I think, hold on. Let's use this. Let's use a trick. Let's say a equals, I don't know, a b c d e f g, a b c d e f g h. So we say a 2, a b c e g. So what if I want to get, so every 2 values I want to get up to 2. No, that's not right. For I in range len word 2, right? And this is just going to be word 2, I to I plus 2. All right? Okay, let me try this. I'm going to say for I in range len a 2, and then we say a I to I plus 2, and let's just do this. That is funny. Oh, of course it's funny because it should be 0. A, B, C, D, E, F, G, H. Yeah, so that's fine. 0, right? So decrypts is going to be equal to this. It's a set, no, a list of sets, right? A list of sets. And then we're going to go through the dictionaries. And we just say Q equals self.dictionary. While Q, not while Q. How many times we have to go through this? We have number of digits, so it's len word 2. So let's call it K. It's len word 2. So while K and Q. Okay, so K and Q both need, any of them become 0, and then we're done. Okay, so then we have a temp. Now we say for word in Q, right? So each word in Q, then we're gonna check. Ooh, let's do it easy. Oh, I. Okay, so 0. So I, while I smaller than K, right? And for each word in Q, we say if word I is, I don't know, in decrypts I, right? If it decrypts I, temp.append word, blah blah blah, Q equals temp. And once they come out, we're going to return len Q. Let's throw this inside. See if it works. Better yet. Something is not right. Oh, I forgot to increment I. I plus equal 1. My bad. String index out of range. Decrypts. All right, this one works. Not sure. Try it. Doesn't hurt. String index out of. Wait, what? Wait, hold on. Oh, it could be larger than. Yeah, look at this. The dictionary is this, and then we're getting these in. Wait, hold on. Let me see the requirements. Would 2 is smaller or equal to 200, but it never says that when it's decrypted, it's going to be the same length as the dictionary. So what we're going to do, we can check. We say if len word is equal to, okay, and so if the length of the word is not equal to, so length of the word is the dictionary. If it's not equal to k, where k is the decrypts, right? If they're not equal, then it cannot be. So if it's equal and this satisfies, then we check. Otherwise, we do not check. Let's try this one more time. One more time. All right, run. Okay. One more time. We passed. We passed. It's not too bad. So, sometimes the hard problem is not that hard. I should say, let me say something. So, the encrypt part is trivial. The decrypt part, is tricky because it is it might be very time consuming, right? Consuming to generate all possible decrypts. However, since dictionary is finite, with at most 100 times 100 runtime to check whether each word in dictionary fits the decrypts. I choose to go from it's fine at most to check each letter. To check each letter in each word, all right, I decided to check whether each word in dictionary fits the decrypts. The checking procedure follows a BFS scheme where we go through each word in dictionary, check whether it has the same length as the decrypts, right? And whether at the current position the word's letter is contained in the decrypts. Any mismatch results in the word being discarded. We run this until either all words in dictionary are discarded, or all positions in the decrypts are checked. So it passed. This method passes. It's not too hard. Yeah, it's not too hard. Runtime. So encrypt is O lan word 1. Initialization, right? So have initialization is on, right? Initialization is on. And encrypts all this, decrypt. Okay, so decrypt, that's O lan word 2. And then the worst case, yeah, let's call it OM. We just can't call it OM plus N. No, I didn't do it in a dictionary. So N equals lan keys. Oh, keys is at most 26, so that's actually O26, right? The most O26. And this is OM, which and the lan word 2. So yeah, we can say lan word 2 plus this procedure. So at most is OM. It's OM, where M is the total number of letters, not words, in dictionary. I bet there are smarter methods. Let's take a look. 28%. Two hash maps. You gotta be kidding me. Decrypt is 01. Oh, are you saying? Oh, wow. Holy guacamole. Oh, yeah. Oh, yeah, I know the trick. And I am here thinking this is a good solution. Nah, man. Screw this. This is much better. Yeah. Why I didn't thought about this. Just encrypt all the words in dictionary and find their frequencies. Thus, in decrypt, we check if word 2 appears as one of the encrypts of dictionary, of the words in dictionary. I hope that makes sense. Wow, that's genius. I don't have to change any of these. We have to change this, right? We have to change this. So what do we change? We just say, yeah, what I call a counter. We need counter, right? So we say self.counter equals counter for word in dictionary, and we just call it self.encrypt word, right? And then decrypts just return self.counter word 2. That's it. Madre mia. Madre mia. How could you be so good? Oh man. I look at it, oh 01. What the hell? 01. Oh, and we don't need this. Like, who needs this? We don't need this. We don't need this. Right? That's it. Oh, you gotta be kidding me. This is so good. Oh man, you gotta be kidding me. Oops. We have a key error. Oh. Wait. So that is the dictionary, right? Wait, hold on. What is dictionary? Dictionary is the word. After decryption. So it has to be inside, otherwise it's not. Hold on. So what you're saying is encrypt word. That should be an empty string. We can say .get. We can do this. That's just fine. Should be 0. Let's put a symbol that definitely is not going to be English letter. There we go. We have to put something that's not an English letter. Oh, so good. Still, there's a little bit of trick here. A little bit of trick here. Well, notice the trick in encrypt. Because there is no guarantee that all the words in dictionary are encryptable. Thus, if any word cannot be encrypted, we simply use a non-English letter, English symbol to represent that, to represent a failed encryption. Since the actual, since word 1, right? Since word 1 is guaranteed to be encryptable, right? As I think it says, it's guaranteed to be encryptable. Yeah. Guaranteed to be encryptable. This trick won't affect encrypt, but it will make the non-encryptable words in dictionary stand out. Then, when we query word 2, if it's not right, when we query word 2, if it's not encryptable, and when we query word 2, all the non-encryptable words in dictionary won't play a part. So good. So good. And so simple. My God. 280 milliseconds. 82% ranking. Oof. Oof. Alright. This one's good. This one's awesome. My Lord, he's good. Oh man. Yeah, you see that? You see this one? Oh man. It's sick. It is sick. Yeah, I know backtracking is not gonna work. I know it. I knew it. I've done enough of this to know that when you have a list of size 100 and you have another possible, you do backtracking or whatever, and you don't know, it's not polynomial, it's exponential, right? You know that it's not gonna be exponential to try to check on a dictionary. It has to be the other way around. But I think like this is like level 1, right? I am on level 1, and then if you cannot do it, it's like level 0, and he's like on level 100. Oh man. Do not generate all the possible strings. Yes. Encrypt the dictionary. Ah, this is so good. Oh my God. Hmm. It is so good. My Lord. So smart. So smart. This is too smart. All right, that's it. That's it for today. I'll see you guys tomorrow. Adios.